will be equal to 1.8 times 10 to the power 3 multiplied by 1.5 3 times. Okay, so this will be equal to 1.8. So it's equal to 8,100 Newton. Okay, so the equivalent load is at 8,100 Newton. And the distance from here to here, this distance will be 1.5 plus by 1.5 divided by 2, right? So this is 1.5 divided by 2 plus 1.5 is equal to 2.25. Okay, so as I said, we want to find the reaction at point A and at point B. Okay, so one way of doing this, okay, so based on symmetrical loading, okay, based on symmetrical loading and geometry, right? We know that AY is equal to BY, right? So this is based on symmetrical loading, symmetrical loading and geometry about the y-axis. So y-axis over here, if we're going to draw, we're going to sketch, this is where the y-axis is, right? So left is equal to right. So AY is equal to BY. So for on this context, you can just do positive using static analysis. So you have AY plus BY minus by twice of 3 times 10 to the power 3 minus by 8100 is equal to 0. Okay, so because AY is equal to BY, 2AY is equal to 3 power 3 times 2 plus by 8100 is equal to 14,100. Okay, so AY is equal to 7050 Newton. Okay, let me do it again. 2 times 3 power 3 plus by 8100 divided by 2. Okay, you can do this, or if you are not sure that AY is equal to BY, right, you can take moment about A with the known distance. Okay, if you are not sure, I'll show you. Okay, so let's say if you can't remember based on symmetrical loading, we can alternative pass number 2. Your answer will be the same. Okay, so we are going to take summation of moment Z. We're going to take at point A is equal to 0. Okay, the answer will be the same. Okay, so we will have so it's going to be going in a clockwise direction. So it's minus 3 times 10 to the power 3 multiplied by 1.5 distance minus by 8100, and the distance we know is 2.25 minus by 3 times 10 to the power 3, the distance is 3, right, plus by 4.5 by. Okay, the whole thing is equal to 0. So by will be equal to 3 power 3 times 1.5 plus 8100 times 2.25 plus 3 power 3 power 3 times 3 divided by, so it's 31,725, and then you divide by 4.5 is equal to 7050 Newton. It's the same. Okay, so don't worry if you don't know about the rules of symmetry. Okay, we are unsure, the answer will be exactly the same. Okay. So from here, we are going to find the load distribution between A to C. Okay, so what we are trying to do down here is we are going to find the bending moment equation. Okay, we're going to find the bending moment equation. So hold on. So we're going to find the bending moment equation. I know there's a lot of recap. Okay, probably you guys have done this in 2P before, but I want you to remember. Okay, so the limit that the limit that we're going to have down here is 0, x, and unto 1.5 meters. Okay, so this is between point excuse me, point A to the next point is our point what? To point C. Okay, point A to point C. Okay, so we're going to draw this out. As I said, we're only interested in the bending moment equation. Okay, so this is our point A. So point A, we have a load over there, right? So this will be equal to 7050. And we have a load coming down. Okay, so this load coming down is 1.8 times 10 to the power 3 x, right? And the distance from here to here is x. And the distance from here to here is x over 2. As I said, we are only interested in moment at point x. So this is where we're going to take our moment. Okay. So from here, we know that we're going to take summation about moment in the z direction at point x is equal to 0, right? So you will have 7050 multiplied by x. So minus, because it's going clockwise, minus 7050 multiplied by x. Okay. Then plus 1.8 times 10 to the power 3 multiply x, right? And then this thing multiplied by x over 2. Okay, and then the whole thing plus by m as a function of x is equal to 0, right? So we can have m as a function of x is equal to, so this will be equal to minus 0.9, right? X squared. I'm bringing it over, right? 0.9 times 10 to the power 3, or I write this 900 and minus 900 x squared. Okay, and then plus 7050 x. Okay, so if we want to find, okay, the moment at point C, okay, we want to find the moment at point C, right? So all we need to do, so I'm going to call this equation number 1. Okay, we're going to substitute x is equal to 1.5 meters into equation number 1. Okay, so moment, so therefore moment about point C will be equal to minus 900 1.5 squared, okay, plus by 7050 multiplied by 1.5. The whole thing will be, so 900 1.5 times 1.5 times 900, okay, then plus by 7050 times 1.5 is equal to 8550 positive 8550 Newton meter. Okay, so let me do it again. So minus 900 times 1.5 times 1.5 plus 7050. Yep, is 8550 Newton meter. Now, this is at point C. Okay, at point C. Okay. So I know the question asked only at point C, but we want to do something further. I want to find where it's at point E. Okay. All right, we're going to find where it's point E. So next thing that we're going to do is we're going to find, right, 1.5 x to 2.25. Okay. So this is between point C. Okay, just to recap the diagram. Okay. So this is between point C to point E. Okay, point C to point E. So the equation will change slightly. Okay, so point C to point E. All right. So now we're going to draw the free body diagram again. So this is our point A. And this is our point C. Right? That's our point C. So we know at point A, we have a load over here, and this is 7050. Is it 7050? I want to be sure. Yep, 7050. Right? Now at point C, you have a what? You have a, sorry for moving up and down, 3000 Newton. Okay, 3000 Newton. Right? So the distance from here to here will be x, right? So we are aware that the distance from here to here, okay, let me make sure, I do apologize, okay? Let me make sure that this does not look like halfway. Or not, wait, you will be confused, okay? So we know the distance from here to here is x, all right? This is 1.5, right? So the distance from here to here is x minus 1.5. And then we have another load, which I'm going to change the color. And this over here is equal to 1.8 times 10 to the power 3x. And the distance from here to here is x over 2. Okay, so that distance, because this distance is x, yes or no? Distance from here to here is x. Okay, so again, positive bending moment assumption. Okay, so from here we're going to form the equation again, right? The trick about doing this is get your load correct and get your distribution correct. Okay, so over here, some mention about moment in the z direction at point x, right? So this will be equal to 0. Okay, so we have minus 7050, right? That is the reaction force at point A, is going in a clockwise direction. Then plus by 900 x squared, right? And then plus by 3000, right? X minus 1.5. The whole thing will be equal to 0. So, yep. So, oh no, got one more, okay? Plus by m as a function of x, okay? Now, I do apologize, okay? This is not C to E, okay? This is C to point D. Okay, this is C to point D. My apologies. And this is x is equal to 1.5 to 3 meters, okay? So it's C to point D, okay? This C to point D. So from here, we have minus 7050x plus by 900x squared plus by 3000x. So 3000